So what is the point in a capacitor? Why go to all this effort to maybe store some charge? Why not just perhaps maybe use a normal cell or a battery instead? Well, this has a number of advantages. First of all, what we can do is we can store a lot of energy and then release it really, really quickly. So this is maybe how camera flashes work. What they do is they take a normal kind of AA battery and they store up the energy and they release it very, very quickly in a small amount of time, which means we have a very, very powerful light source. And what we can look at now is the energy stored by a capacitor. Now in my circuit, what I can maybe look at is the potential difference that I have across that capacitor, as well as the actual total charge stored. And effectively, when I have a greater source of EMF, I have a greater potential difference across the component, and that means it then stores more charge. And if I actually look at this with a graph, what we find is that we have this nice kind of linear relationship, that as you increase the potential difference, more and more charge is stored. But if you have more charge stored in the capacitor, that means it's also storing more energy. And in actual fact, the energy is equal to the area under the graph. Now, the energy stored is effectively the amount of work that can be done by the electrons which are stored within it. And because it's the area under a graph where we have this nice linear line, energy, which we give the symbol W to, is going to be equal to the area of this triangle, which is equal to a half QV. Okay, and this is one of the first equations that we can use to work out the energy stored by a capacitor with a certain amount of charge stored on it and also held at a certain potential difference. So this is the energy stored by a capacitor, but we also know that the capacitance is equal to the charge stored per unit potential difference. And if we rearrange this to make V the subject, we can say that V is equal to Q over C. And therefore what we can then do is maybe rearrange this by putting this, replacing this V term here with Q over C. And therefore we can also say then that the work done is equal to a half multiplied by Q squared over C. And this is our second equation. The other thing that we can do is we can rearrange this to maybe say that Q is equal to CV. And if we replace the Q with our CV term, we can also then say that W is equal to a half times, well, it's going to be CV multiplied by V, so half CV squared. And these three equations here let us know how much energy is stored by a capacitor in terms of the charge and the potential difference, the charge and the capacitance, or the capacitance and the potential difference squared. So these are just based on the graph that we saw in that last part of the video, and also the equation that defines our capacitance of a capacitor.